Right, for our second video, we're going to review the Pythagorean theorem and how to use it. Now remember, the Pythagorean theorem only works for a right triangle like this one. We have the right angle here, so that's 90 degrees. We call the side that is across from the right angle the hypotenuse, and we normally refer to that as C. The other two sides, this one and this one, we call legs, and we call them A and B. Now, if you don't want to call that one A, you can call this one B and this one A. It really doesn't matter. A and B can be switched around. C always has to be this hypotenuse, though, the one across from the right angle. And that's because if we write out the Pythagorean theorem, it's a squared plus b squared equals c squared. Now, A and B can be flipped around. So if we do like 3 squared plus 4 squared equals, I'm going to make a better 4, 5 squared. This is true because 9 plus 16 is 25. We can switch those two around and call them 4 squared plus 3 squared equals 5 squared. And that is true. It just means that this C value always has to be the biggest length, the hypotenuse. C is always the hypotenuse across from the right angle. These two you can switch around, but then the Pythagorean theorem has to be a squared plus b squared equals c squared. Now let's see how that works using some of our examples. So we're just going to be solving for the missing length, and we're going to leave our answers in exact form. So not rounding to any sort of weird decimals. We're going to leave it in the exact form. So for example 1, we have one side length of 6, one hypotenuse of length 10, and a missing side b over here. So we would just plug it into our Pythagorean theorem, a squared plus b squared equals c squared. So 6 is a, we call it 6 squared plus b squared equals, our hypotenuse is 10 squared. Now all we have to do is simplify. 6 squared becomes 36, b squared stays the same, 10 squared is 100. If we subtract 36 from both sides, we'd get b squared equals 64. Now to undo a squared, we would take the square root of both sides. And if you remember from before, when you take the square root, we have to do a positive or a negative. Now in this case, though, if we think about it, would it make sense to say that this is a negative somewhat inches? Like depending on how many numbers it is, whatever, a negative length doesn't make sense. So we really don't have to worry about the positive or negative side of things. We're just looking at the positive amount. So when we do the square root of both sides, we get rid of it, and we find just simply b equals 8. So we have 6, 8, and 10. We found our missing length. Let's look at another example, example 2. In example 1, we had the hypotenuse and one leg, and we found a missing leg. In example 2, we have the 2 legs, and we're missing the hypotenuse. So when we set it up, it would be 5 squared plus 12 squared equals c squared. Simplifying that, 5 squared is 25, 12 squared is 144, so 25 plus 144 equals c squared. Add those up and we get 169 equals c squared. Well, how do we get c alone? Again, we take the square root of both sides. Now, normally, again, we'd think positive or negative, but because this is a length, it doesn't make sense to have a negative length. So we would just simply say c equals 13. So we have 5, 12, and 13 as our lengths. All right, for example 3, we have this isosceles triangle, 5 centimeters over here, which means this one is also 5 and 8 all the way across. Now if this is 8 centimeters all the way across, and we want to find this up and down length, the height, that means we're going to need to know just one of these lengths over here. So if the whole thing is 8, just one of these is 4. So we have 5, 4, and a missing length, 5 being hypotenuse. So we'd call it 4 squared plus b squared, whatever this value is, equals 5 squared. That's the hypotenuse again. So it's like we're basically, I'm going to use a black shade here. We're going to cover that up. We're just looking at this triangle now. 5, 4, and whatever our missing value is. So simplifying that out, 4 squared is 16, 5 squared is 25. So 16 plus b squared equals 25. We have to subtract 16 from both sides, and we get b squared equals 9. To get rid of that squared, we'd have to take the square root of both sides. Now again, normally we'd do positive or negative, but these are lengths, so we just want positive, so we'd say b equals 3. So if this is 5, this is 4, this one has to be 3. So everything fits. Example 4. Again, we have a hypotenuse of 12, one length of 8, and a missing length of x. X and 8 are two legs, 12 is hypotenuse, so when we plug it in, it becomes 8 squared plus b squared equals 12 squared. Now instead of saying b, I could have called it x, because I guess we put an x in this case. So we can say that just as easy. So 8 squared plus x squared equals 12 squared. Simplify everything out. 8 squared is 64. X squared, I guess we call, or leave it as x squared, or b squared, whatever we want to call it. And 12 squared is 144. Subtract 64 from both sides and we get b squared, or x squared, whatever you're going to call it. You can rename it x if we want. X squared equals 80. Now again, to get rid of that square root, we would have to take the, or to get rid of that squared value, we'd have to take the square root of both sides. So this side's just going to become b, or x, whatever you want to call it. We can call it x if we want. And this would just be the square root of 80, because that one does not simplify down, or it does not have an exact answer. But, as we saw before, we know how to simplify any square roots. So we're going to have to simplify this square root of 80 down into square root of 16 times the square root of 5. Simplify that to 4 square roots of 5. So our missing value would be 4 square roots of 5, which is the same as saying the square root of 80. In this example, we can see that we have two different missing values. We have x is our hypotenuse, and x minus 2 is this leg. So when we plug everything into our Pythagorean theorem, we get that this length, or this leg, plus squared, plus this leg squared equals this hypotenuse squared. So 4 squared plus the entire thing, x minus 2 squared, equals x squared. Now, when we do x minus 2 and we square it, what we're saying is we're doing x minus 2 times another x minus 2. So it looks something like this, which means we have to FOIL x times x times negative 2, negative 2 times x, negative 2 times negative 2. X times x makes x squared. X times negative 2 makes minus 2x. Going with negative 2 times x, we have another minus 2x. Negative 2 times negative 2 is positive 4. So this piece is all of this, and then we would combine like terms if we can. So let's simplify everything from here as we can. 4 squared becomes 16. X minus 2 squared becomes all of this, and notice that these two can combine to minus 4x right here. X squared minus 4x and plus 4. And we still have an x squared over here. At this point, we'll combine any like terms. We're also going to do minus x squared from both sides, which means this will cancel out and this will cancel out, and we're just left with a 0 on this side. So at this point, our equation would say negative 4x plus 20 equals 0. Now how do we get rid of or move one of these to one side or the other? Well, we could add 4x to both sides, meaning we'd get rid of it here and do plus 4x over here. So it would look like this. 20 equals 4x. Then we just divide both sides by 4, and we'd get that 5 equals x. Which means, looking back up here, if 5 was x, we would have 5, 4, and 5 minus 2 would be 3. So we'd have 3, 4, and 5 as our side lengths. Now we have a couple of word problems here. It says the foot of a ladder is placed 6 feet from a wall. So if here's a wall, we'll go like this. The end of the ladder is 6 feet away. So we're going to come out. This is where the ladder is placed. It is 6 feet away. The top of the ladder rests 8 feet up on the wall. So the top of the ladder goes right here, and this is going to be 8 feet. So our ladder looks something like this. It's the red line there. And we don't know how long the ladder is, but that's what we're trying to find out. So we use the Pythagorean theorem to say 8 squared plus 6 squared equals c squared. 64 is 8 squared. 36 is 6 squared. So 64 plus 36 equals c squared. 100 equals c squared. Like before, we'd have to take the square root of both sides, and we would get that c equals 10. So we would say that Our ladder is 10 feet tall. In the Old West, settlers often fashioned tents out of a piece of cloth thrown over tent poles, then secured it to the ground with stakes forming an isosceles triangle. So here would be our pole, here would be our two stakes, and then the cloth would go over the top like this. And then, of course, we have our ground. So that would make our tent then. How long would the cloth have to be so that the opening of the tent was 4 meters high and 3 meters wide? Well, that means from here to here, it's 3 meters wide. This tent here would be 4 meters high. And ours isn't necessarily drawn to scale, but this is how it would look like. So we want to find the whole length of this cloth. Now, we might not be able to find the whole length of this cloth, but we could find at least one of them, like 1/2 of it, and then just multiply it by 2. So if we were to stop right here, make a right triangle on this side, if the whole thing is 3, then just this half would be 1.5. Now we can find this half over here of our cloth. So we would plug everything in and say 4 squared plus 1.5 squared equals c squared. So 16 plus 2.25 equals c squared. So 18.25 equals c squared, which means in the end that square root of 18.25 equals c. Now, we can leave it in that decimal form and say that that's that half over here, and then say just simply the whole length of that, if this is just 1/2, is square root of 18.25, then the whole length would be 2 square roots of 18.25. How do we know? Well, because we'd have 1 over here and 1 over here. So 2 square roots of 18.25 would be our whole length across of the tent. In example 7, we're looking at defining whether or not we have right triangles. Now, the only way that these lengths would form a right triangle is if the two smaller ones, 3 and 4, if we added them together after squaring them, so 3 squared plus 4 squared, if it did in fact equal 5 squared. So as long as you can check those answers and those numbers and they do match up, that means we do have a right triangle. So let's check these ones. If we have 3, 4, and 5, the two smaller are 3 and 4, so we'd say 3 squared plus 4 squared equals 5 squared. Simplify that. 9 plus 16 equals 25. 9 plus 16 is in fact 25, so we're saying 25 equals 25, which is true. So yes, these would make a right triangle. Let's look at these lengths, square root of 3, square root of 5, and square root of 8. We would use the two smaller ones, square root of 3 and square root of 5, and see if they add up to the square root of 8. So square root of 3 squared plus the square root of 5 squared equals the square root of 8 squared. Well, each of those would just become 3, 5, and 8. So 3 plus 5 equals 8. So we're saying 8 equals 8, which is true, so yes, these would make a right triangle. In this triangle, we have 5, 11, and 13. So these are two smaller ones, 5 and 11, equaling the bigger one, 13. So 5 squared plus 11 squared equals 13 squared. 25 plus 121 equals 169. 25 plus 121 is 146. Does it actually equal 169? No, it does not. So no, these three would not make a right triangle. If you have these lengths, like 5 feet, 11 feet, and 13 feet, you cannot possibly make a right triangle unless you were to cut one of them up. So no, those do not make a right triangle. Pythagorean triples are the last piece of our of this video. Pythagorean triples are any sets of 3 numbers that could make a right triangle. Now the two that I want you to be most concerned about are these, 3, 4, and 5, and 5, 12, and 13. These sets of numbers will always be able to make a right triangle. And how you know that is 3 squared plus 4 squared equals 5 squared, or 5 squared plus 12 squared equals 13 squared. Now, here we have some other ones that would work, like 7, 24, 25, or 9, 40, 41, or 20, 21, 29. All of these are sets that would work, but I mainly want you to be concerned about these ones. Try to commit these ones to memory, especially the 3, 4, 5. 3, 4, 5 right triangles are going to come into play a lot, and it'll be very helpful for us to see if we know that we have a ratio of 3 to 4 to 5. Well, let's pretend we doubled all of that. 6, 8, and 10, that also counts as a Pythagorean triple. 6 squared plus 8 squared does equal 10 squared, so that counts as well. This would make a right triangle. Let's say we multiplied each of these numbers by 4. We'd have 12, 16, and 20. And in fact, yes, those would make a right triangle as well. So remembering 3, 4, and 5 do make a right triangle, and then just think, well, I can do different multiples of that, so like double them or triple them or quadruple them, then yes, all of those sets would be Pythagorean triples, or in other words, they would make right triangles. And that'll end it for our video on Pythagorean theorem.